So we're going to be going over transformations and asymptotes today. So what does that include? It includes rational functions, the horizontal and vertical asymptotes of rational functions, which is a super, super common exam question. Then we're going to talk about transformations of functions. So a f of x plus b, that sort of thing, shifting left and right, shifting up or down. That's all standard level content. Then in about an hour, we'll get to the higher level content, which includes further transformations. So combining horizontal translations with horizontal scaling. Yeah, we'll do absolute value transformations. We'll do square transformations. We'll do 1 over f of x. And then we'll also do, even though it's not super common, it is on the syllabus, the asymptotes of rational functions with quadratics. So oblique asymptotes, when you have a numerator that's a quadratic or a denominator that's quadratic, and therefore you get two asymptotes. So we're going to cover all of that. And it's a lot of material, so we should get started straight away. The reciprocal function is the function f of x equals 1 over x. All right, and we notice that f of x is not defined for x is equal to 0 because 1 over 0 is undefined. But 1 over x does get very, very large as x approaches 0, and we know that f of x is going to have a vertical asymptote at x equals 0, which just means that as I get closer to 0 from either side, I'm going to have this behavior where the value of the function gets infinitely large or infinitely small, but I also cannot have f of 0. I can never actually reach that point. Okay, so that means I have an asymptote at x is equal to 0. Similarly, I have a horizontal asymptote at y is equal to 0 because as x gets very large, I'm doing 1 divided by a very large number will get smaller and smaller, but it will never be 0. 1 divided by something can never be 0. All right? One important fact to remember is that the function f of x is self-inverse, which means if I do f composed with f, I get back x. And you can see that if I do 1 divided by x, I get x. That makes f of x self-inverse. You can also see it on its graph. Remember that the graph of the inverse function is the reflection of the original function in the line y is equal to x. So you can see that the function 1 over x is symmetrical in the line y is equal to x. So when I mirror it, I'm going to keep the same line. And that means it's a self-inverse function. Now, the graphs of linear rational functions. Suppose that you have a function in the form ax plus b over cx plus d. Okay? We know, similar to what we said on the previous slide about reciprocal functions, that when the denominator is 0, I'm going to have a vertical asymptote because I can't have something divided by 0. Okay? When does that happen? It happens when cx plus d is equal to 0, which means x is equal to negative d over c. And it looks a bit weird maybe with specific, with variables, but I'll show you an example with numbers in a second and it'll make more sense. Now, as x gets very, very large, the plus b and plus d kind of become irrelevant. So I want you to imagine in this expression that I put in 10 to the power of 20. So I put in x is equal to 10 to the power of 20. So then f of x is equal to a times 10 to the power of 20 plus b divided by c times 10 to the 20 plus d. And obviously, b and d could be pretty big. But the point is, I can always choose an x that's big enough to make b and d be like absolutely tiny compared to a times 10 to the power of 20 and c times 10 to the power of 20. And basically, for a very large x, this is just going to be approximately a over c. Okay, so as x gets large, the b and the d become less important, and I get closer and closer to a over c. But again, I'm never going to equal a over c because the b and the d are not actually 0. It's just that they become less and less significant and basically insignificant for large x. So what's the behavior I see? I see that I have a horizontal asymptote at y is equal to a over c. Okay? Neither of these formulas are in your formula book, unfortunately, but they are pretty intuitive to remember. When the denominator is 0, that's x equals negative d over c. I get a vertical asymptote. And I think about what happens when x gets very large. Well, I ignore the constants, and I get a horizontal asymptote. Now, it's worth getting it clear in your head because the horizontal asymptote has an equation y is equal to something, and the vertical asymptote has an equation x equals to something, even though we associate y with the vertical direction and x with the horizontal direction. And that's because a horizontal asymptote like y is equal to something, is a horizontal line, which means it has a constant y. It actually goes through every x value, and so we have to define it by y is equal to something. And you have something similar for vertical asymptotes. Okay, let's do an example. I want you to find the equation of the asymptotes of 2x plus 1 over x minus 3. Well, the first thing I notice is that the denominator is going to be 0 when x is equal to 3. So I have a vertical asymptote at x is equal to 3. And then, because I have 2x divided by x, let's say I imagine plugging in a million for x, I'm going to get 2 million plus 1 divided by a million minus 3, and that's going to be basically 2. So I'm going to have a horizontal asymptote at y is equal to 2. So I'm going to give you a minute to do this exercise. I want you to sketch the graph of y is equal to 3x minus 2 over x plus 2. These you can drag around until you get them in the position that you want, and then you just hit grade to submit your answer. Okay, so I'm going to give you maybe a minute for this. Okay, let's go over how to solve this. All right. So the first thing I want to think about, the easiest thing to think about first, is the denominator to find out when I'm going to have a vertical asymptote. So I have x plus 2 in the denominator, and that's going to be equal to 0 when x is equal to minus 2. So my vertical asymptote has to be at x equals to minus 2. Let's move it over there. X equals minus 2. What else do I know? I know that I have a horizontal asymptote. If I look at the leading coefficients, I have 3x divided by 1x. So I'm going to have a horizontal asymptote at 3. And I'm just going to move this out of the way, otherwise it's going to be confused. And now the last thing is to figure out where this y-intercept is going to go, right? So the y-intercept, remember, is the value that the curve or function takes on when x is equal to 0, because that's what the y-intercept is. It's the line where x is equal to 0. So if I plug in 0, I'm going to get, well, 3 times 0, just negative 2 in the numerator, and plus 2 in the denominator. That's going to be minus 1. So my graph should look something like this. How do you know which way the graph is? I don't know how to describe it, but why is the graph looking like that and not reflected in the horizontal asymptote? So are you saying, I think what you're maybe saying is, how do I know it's, maybe we were on the previous slide when this question came up, so let's go back there. How do I know it's this way and not this way, right? How do I know on which side of the asymptotes my arms are going to be? And the best way to do it, honestly, is, I think, to think about where the y-intercept is. Because once you know where the y-intercept is, it automatically tells you everything else. So in this case, I have the function 2x plus 1 divided by x minus 3. So if I put in x is equal to 0, I'm going to get 1 over minus 3, which gives me negative 1 over 3, which tells me my y-intercept has to be somewhere down here. And notice that that is below the horizontal asymptote. And since the function can't cross the horizontal asymptote, at least this one can't, I must be below the first arm. And because I know that the sign is going to change when x is equal to minus 3, it has to be positive afterwards. You can always, by the way, plug in specific values of x to check, oh, is it positive? Is it bigger than my asymptote? That's totally fine. And in fact, I would encourage you to do that if you're ever not sure about where the arms are. More Q&A. Is the horizontal asymptote a over c, or so the line y is equal to a over c is the horizontal asymptote. Oh, I guess you're confused because I put vertical on the slide. That's yeah, that's true. This is supposed to be horizontal. Well spotted. I'm sorry about that. There's a horizontal asymptote there. Apologies, but yes, well done. And then, how did you get the y-intercept again? Okay, let me go to the next slide. So I got the y-intercept, remember, by plugging in x is equal to 0, because the y-axis is the line x is equal to 0. That's the definition of the y-axis. So I plugged in x is equal to 0 into this expression. I got minus 2 over 2, so I did 3 times 0 minus 2 over 0 plus 2 is equal to minus 2 over 2, and that is minus 1, right? So minus 1, okay. Another exercise. This time I'm giving you the graph and all the information about it, and I want you to find the value of a, b, and c in the function. All right, so let's go about solving this. The first thing we want to find here is the value of a. And the way we're going to do that is to think about the horizontal asymptote, which we see is at y is equal to 3. And we remember that I have a horizontal asymptote at a divided by the leading coefficient of the x, which in this case is 1, because I have a divided by 1. And that's where I'm going to have a horizontal asymptote. Okay? And I know that that is y is equal to 3, right? That's what I see on the graph. And therefore, I know that a must be equal to 3. Okay? Now for b, okay, I have ax plus b divided by x plus c. We're actually going to need to find c first, I think. And to find c, we're going to use the vertical asymptote at x is equal to minus 2, which means that x plus c is equal to 0 when x is minus 2. So minus 2 plus c is equal to 0. That is where I get a 0 denominator and therefore a vertical asymptote, which means that c is equal to 2. That's c is equal to 2. And then for b, the graph is giving us the horizontal, the x-intercept. So I have an x-intercept at minus 2 over 3, which means if I plug in x equals negative 2 over 3, I should get 0 for f of x. So f of negative 2 over 3 is equal to 0. What does that look like? Well, if the something divided by something is 0, it's because the numerator is 0. So a times minus 2 over 3 plus b is equal to 0. And that means, because I found that a was equal to 3, that negative 2 plus b is equal to 0. All right? And if negative 2 plus b is equal to 0, then b is equal to 2. Okay, we're going to do an IB style problem now. So I'm going to give you 3 minutes to try this on your own, and then I'm going to continue with the solution. Okay, let's go over the solution to this. So I have g of x is equal to 7 minus 4x over 3 plus 2x. And the first thing I'm looking for are the axes intercepts. So I have two kinds of axes intercepts. I have x-intercepts, which are when the function is 0, and I have y-intercepts, which are when x is 0, and I find the output of the function for that. Let's start with the easier one, which is the y-intercept, which is when g is 0, and that's going to give me 7 minus 4x doesn't do anything because it's 0, and then divided by 3. So 7 over 3 is my y-intercept, and the question wants coordinates, so I have to put 0, 7 over 3. Okay? Now, to find the x-intercept, I'm going to say g of x is equal to 0, and that means that the numerator is equal to 0. 7 minus 4x is equal to 0. Now, that means that 4x is equal to 7, or in other words, x is equal to 7 over 4. Again, putting that as a coordinate, that gives me 7 over 4, 0. So that is my answer for part AII. Now we want to find the equations of any asymptotes. So I'm going to have a vertical asymptote when the denominator is 0. So 3 plus 2x is equal to 0, which means that 2x is equal to minus 3, or in other words, x is equal to minus 3 over 2. That is the vertical asymptote. And I'm going to have a horizontal asymptote when x gets very, very large, and I compare the coefficients of the x's in the equation. So I have y is equal to minus 4 over 2, which is just equal to minus 2. Okay, so that is my vertical asymptote. So those are my answers for AI, AI, and AII. So now we want to sketch the graph of y is equal to g of x. So let's put down everything I know. I'm going to have a vertical asymptote here at x equals negative 3 over 2. Then I'm going to have a horizontal asymptote here at x is equal to negative 2. So let's label those. And just for the sake of drawing the sketch a bit better, I'm going to draw the line y is equal to minus 2 here. So y is equal to minus 2, x is equal to negative 3 over 2. And I know that I have a y-intercept at 7 over 3, so maybe I'll put that there. 7 over 3 is slightly more than 2, so if I want to draw to scale, I should draw slightly higher than this distance. But you don't really have to worry about that. Roughly here, though. And then I have a x-intercept at 7 over 4. So let's say 7 over 4 is here, roughly. Okay? that means I know that on this side it's going to be positive. So I can draw this, getting closer to my asymptote. And on the other side, it's going to have the opposite sign, right? Because uh, 3 plus 2x changes sign here, and 7 minus 4x changes sign here. So on this side, it's going to be over here. And one way I could check that, if I go to the left of my vertical asymptote, I could take x is equal to -2. I could plug that in. I'd find g of -2 is equal to 7 plus 8 over 3 minus 4, and that would be equal to -15. And that would tell me that I have to be negative and below my horizontal asymptote. Okay, so this is the sketch, and make sure you say that this is 7 over 3 and 7 over 4. Because we found them, we now have to include them in our sketch. Oh, so okay, that was the only example I wanted to do of the very basic linear rational functions. We'll do more types of rational functions for higher level students. For SL, it's kind of just this. The question might be combined with some inverse function ideas or something like that. But for the most part, that's all you need to know about rational functions. At the higher level, there's going to be more, but we'll get to that later. The next topic is transformations of graphs. So we're going to start with, I think, the easiest one, which is the vertical scaling of graphs, right? So if I have a function f of x, then what is the graph of y is equal to a f of x going to look like? Well, remember that the graph of a function is the set of points x comma f of x, the set of inputs to outputs, and we plot those on a curve. And doing af of a is the same as putting or multiplying all of those y coordinates by a. So I'm not changing any of the x coordinates, but all the y coordinates are going to be multiplied by a. And the result of that is a stretching or scaling of the graph by a factor of p. So you can see here the original graph in a dotted line and what the graph of p times that would look like depending on the value of p. Now, it's important to know that sometimes p can be less than 1, right? P can be like 1 over 2, which would be a compression. It would be kind of squeezing the graph back on itself. In IB, it's always safest to use the word vertical scaling by a factor of whatever it is. So that's what you should write if you're trying to describe the transformation on an exam. You should say a vertical scaling by factor p. Other types of transformations, vertical translations. So if instead of doing y is equal to a f of x, then I would have y is equal to f of x plus b, which means whatever y value I have, I'm just going to add b to each one, which means I'm shifting the entire graph up or down if b is negative by b. Why not compression / stretch? Look, you can use them. You might not use points. Some teachers and some examiners are really, really strict about the words here. And also, compression / stretch, you're kind of doing more than you have to do because you don't even need to decide whether it's a compression or a stretch. If you just say it's a vertical scaling by factor of 2 or 1 over 2, you've kind of automatically taken care of it, and you don't really even have to think, oh, is it a compression or a stretch? Okay, so I would recommend just saying scale. Now, horizontal translations. This one is a little bit harder to think about because if I have the graph of y is equal to f of x minus a, that's going to correspond to a horizontal translation of a units to the right, which doesn't make any sense. Why am I adding plus a to all the x values if I have x minus a inside of the function? So again, what I want you to remember is that a function is nothing more than a series. The graph of function is nothing more than an infinite set of points on the graph. Okay? And each of these is x comma f of x. All right? So I want you to imagine now that we are graphing f of x minus a. And let's say that we pick an x value. Can I draw this better? I can. Let's say we pick an x value that is, I don't know, here, okay? Let's say we pick x here, and then x minus a is over here. So this is x and x minus a. So we go and we find f of x minus a is here. That's f of x minus a, the value. But we are now plugging in x into f of x minus a, which means the x coordinate of this new function that I'm plotting has to just be x, which means I'm going to take this y value that I found, but move it to the x value that I have, which is here. Okay, and that's why we're shifting to the right, because basically what's happening when we're graphing f of x minus a, we're essentially graphing what was the x value, the y value of the graph a units to the left. What was it when I was at x minus a compared to where I am now? Which means that I am now a units to the right of every point that I am reading from the graph. Okay. All that to say that when I have a translation of the form f of x minus a, that means a horizontal translation a units to the right. So just remember that it's to the right for negative, and if I have a plus, then I'm going to the left. Okay? Now, horizontal scaling, all right? So if I'm graphing y is equal to f of qx, then what I'm going to be doing is a horizontal stretch or a horizontal scale by factor 1 over q. Okay, so what does that look like? Let's say I do f of, yeah, you can look at this image here, right? I'm graphing f of qx in green and then f of x as the dotted line. As q gets bigger, you see that the function is being more and more compressed, and I'm saying compressed here. You can use it if you want, but that's equivalent to scaling by 1 over q, right? Because compression is the opposite of stretching. So you can just describe this as a scale with factor 1 over q, all right? And this is what they want you to say. They want you to write this 1 over q on exams when you're describing this. They don't want you to say compression by factor q. You're supposed to say stretch by factor 1 over q or scale by factor 1 over q, all right? Now, little IB question. I'm going to give you, let's say, 4 minutes to try this on your own, and then I will go over the solution with you. So I'm trying to graph y is equal to 2f of x plus 3 minus 1. And we want to clearly indicate what happens to the point A prime, which corresponds to point A. So the image of A under the translation. So let's start by understanding what the translations are going to do. So the x plus 3 means a horizontal translation. I'm not going to write the word translation because it takes me a long time to write anything on my iPad. So it's going to be 3 units to the left. 3 to the left. Okay? And then the 2f gives me a vertical scale by 2, by factor 2. And then the minus 1 at the end is a vertical shift or translation by 1 unit down. Okay? So let's start by taking A, and we're going to move it 3 units to the left, so it comes over here. That's the step 1. Step 2 is to double it, the y value, and step 3 is to move it down. It's very important that you do the scaling before you do the subtraction, because I have 2 times f and not 2 times f minus 1. Okay, so now I'm going to take this, it's at y is equal to 2. I'm going to double it, and that brings it to here. And then finally, I subtract 1, and that's going to bring it to here. So that is where A is going to be. So let me just now erase and write down where it is. It's at -5, 3. So this is A prime. Okay, that's very useful. Now I can think about the rest of the function being shifted 3 units to the left. So it's going to start, instead of starting at -4, it's going to start at -7. And instead of ending at 4, it's going to end at 1. Okay, it's also going to be 2 times taller and 1 unit down. So if I take this point and move it 3 to the left and then move it, I multiply it by 2, it doesn't go anywhere, and I just move it down by 1. So this one is going to come here, so the function is going to start there. It's going to go up to A. We know that between A and here, it just goes across because horizontal stays horizontal under this kind of transformation. Okay, so then it's going to go like that. And then this point here, which is at 4 minus 1, I move it 3 units to the left. It's going to be somewhere here. Then I double that, that comes here. I subtract 1, and that's going to be here, okay? So let me just draw that last bit. All right. So A prime, I'm just going to write it for the sake of this is what you should show on your exam, that it's at -5, comma 3. Even though there's a grid, it's always safer to just write what you found for the coordinates of A prime. And is there a Q&A? How did you do the vertical stretch? Okay, so in this case, I kind of did it point by point, but what's going to happen when I do a vertical stretch is the whole thing is going to become 2 times as tall. It's going to become literally just vertically more spacious, okay? So one way to think about this is that the minimum and maximum spread was 3 before, and it's going to become 6, right? This is 6 afterwards. So the whole thing is going to be just going to be vertically stretched. I did it honestly by thinking about the specific points where the corners of the original function were, so I could connect them together. A prime was easy to do. This one, I shifted to the left first, but then I multiply it by 2. It's just 0, so I didn't do anything. And I shifted it down, and I got to -7, comma -1, so that was like that. And then this point, I also shifted 3 to the left. I multiplied it by 2, and that got me to -2. I subtracted by 1, and that got me to -3, okay? And now, in part B, the question says that a function g of x is equal to a f of x plus b can be obtained from the graph of f. So f becomes g by vertical plus 2. So vertical plus 2 should probably, yeah, and then a vertical scale times 3 in that order, okay? Which means first I added 2 and then I added 3. So if I do that in order, it means that I can write g of x in the form 3 times f of x plus 2. And I put it in brackets because what happens in brackets happens first, okay? So f of x plus 2, and if I expand this, I get 3f of x plus 6, which means that a is equal to 3 and b is equal to 6. Okay? That's the answer to part B. Why the brackets? Oh yeah, okay, let me go back. So the brackets are because I'm doing the vertical translation before the vertical stretch. So it's followed by. If I don't do the brackets, then we know from order of operations that multiplication happens before addition. But here I can see that I want to do the addition first. The question clearly says addition first, so I have to put brackets, okay? Oh, let me erase. And this is a kind of how much time do we have? We have enough time. This is a classic kind of SL section B question, so one of the harder questions on the standard level exam involving quadratics and transformations. Something like this could show up on HL, but it wouldn't be. I wouldn't call it a hard question for higher level students. So I'm going to give you guys 5 minutes to get a head start on this. I'm not going to let you do the whole thing. Just get ahead of me, and I'll catch up. All right, I'm going to start solving this now. So I have the quadratic function f of x is equal to -3x squared plus 18x minus 15. And I know that it can be expressed in the form f of x is equal to a x minus h squared plus k. That is the vertex height form, which I can obtain by completing the square. So how do I do that? I start by considering where the axis of symmetry is. So I find the axis of symmetry, and the axis of symmetry is at x is equal to -b over 2a, which in this case is -18 over 2 times 3, and that's, sorry, 2 times -3, and therefore this gives me -18 over -6 is 3, all right? So that means that f of x is going to be something x minus 3 squared, and the something that goes in front is the coefficient a, so it's -3. And all I have to find is the plus k. How do I find plus k? Well, if I was to expand the constant terms here, I would get -3 something plus 9, if I squared everything, plus k. And the constant, So if I did f of 0, I would just get negative 3 times 9 plus k, and that's supposed to be equal to minus 15. So minus 27 plus k is equal to minus 15, which means that k is equal to 12. Okay? So f of x is equal to minus 3x minus 3 squared plus 12. That is the answer to part A. Check for questions. Okay, that was part A. Now in part B, I'm trying to find on the graph of y is equal to f of x the coordinates of the vertex and then also the axes intercepts. All right, so I now have f of x is equal to negative 3 x minus 3 squared plus 12. And that's the vertex height form, which means that I know exactly where the vertex is. Remember that when I have the form a x minus h squared plus k, I have a vertex at h comma k, because the vertex happens when this term inside is 0, in which case the only thing that's left for the y is k, okay? So h comma k. So in this case, the vertex is at 3 comma 12. That is the answer for BI. And now we're trying to find the axes intercepts. All right, axes intercepts. One of them is the y-intercept f of 0. That just gives me 12. So I'm going to put 0 comma 12. That's one axis intercept. So just to make it clear that it's the y-axis, the y-intercept. Now the x-intercepts are when f of x is equal to 0. Or in other words, 12 is equal to 3x minus 3 squared, because this is equal to 0. And I move the minus 3 to the right-hand side. If I divide by 3, that means that x minus 3 squared is equal to 4. Square rooting both sides with a plus or minus, x minus 3 is equal to plus or minus 2. So the two solutions I get from that are x is equal to 3 plus 2 or 3 minus 2. So that's 1 or 5. So those are my axes intercepts, all right? Let me erase that, and we'll continue with part C. So I have a description of the graph of G and how I get it from the graph of F. So I'm going to do a vertical stretch by a scale factor negative 2 over 3, followed by a translation of negative 4, 7. So this notation is the vector notation for the translation, and it means an x translation, a horizontal translation of minus 4, so 4 units left, and then a vertical translation of 7 units to the right, okay? So the first thing I do is a vertical scale by factor negative 2 over 3. So g of x, first I multiply, I do times negative 2 over 3, all right? And then I go 4 to the left and 7 up, okay? And that will get me to, sorry, it's the other way. So it's G here, and this is F. So I get from F to G. All right. So to go, if I write this out, I can write G of X is equal to minus 2 over 3 f of, and we'll figure out what the inside is in a second, but then plus 7. So that's the vertical part sorted, okay? And the only part question is what happens to get a a horizontal translation of 4 units to the left, all right? If I have a minus 4 here, then I'm doing x minus minus 4 inside the brackets, so x plus 4 inside the brackets. And therefore, that is the expression of g in terms of f, but I don't want g in terms of f, I want just g, all right? Now I'm going to use what I know that f is. F is, I'm going to use the form negative 3x minus 3 squared plus 12. And if I plug that in, I'm going to get negative 2 over 3 times negative 3x. And now I'm going to put in x plus 4 for x. So x plus 4 minus 3 is because I put x plus 4 in here. All right. That's all going to get squared, and I'm going to add 12. That's the inside. That's f of x plus 4, and then plus 7. All right. If I kind of expand this as much as I can, minus 2 over 3 times 3 is just going to give me 2. So I'm going to have 2. And inside the brackets, x plus 4 minus 3 is x plus 1 squared. Then I have minus 2 over 3 times 12. That is negative 8. So minus 8 plus 7. So this is 2 times x plus 1 squared minus 1. That is my final answer. Okay. And was there an easier way to do that? Yeah, honestly, I might have been able to do that easier. And let me show you how I could have done that better. It was a better strategy there, which was to realize that this function, the original quadratic, we said had a vertex at 3, 12. And I'm translating that vertex minus 4, 7. So it becomes a vertex at minus 1, comma. Oh, wait, no, that doesn't quite work because that's probably more complicated because I have to multiply it by negative 2 over 3. So it becomes negative 8 plus 7. So a vertex at minus 1. I don't know if that's actually any easier, but you can do it this way by thinking about what happens to the vertex and then putting a minus 2 over 3 times the 3 in front. But that might honestly be harder. It's sort of a personal preference thing. Okay, the next kind of transformation that we have to talk about are reflections in the y-axis, okay? So this happens when I have the graph of y is equal to f of negative x, because whatever I'm putting in for x, because there's a negative in front, let's say I'm looking for the value of x here, I need to go to the negative of that value, which is over here, and see what the function's value is there. And that is how I get the y value, okay? So that's kind of the procedure for what's happening when you're graphing f of minus x. But all you really have to think about is the fact that it's a reflection in the y-axis, okay? Okay, we also have reflections in the x-axis. That's what happens if I put the minus outside of f of x, okay? If I do negative f of x. And you can think about this kind of like a vertical scale or a vertical stretch, except that I'm stretching by minus 1. So the whole thing is going to flip to the negative side. Every y value gets multiplied by negative 1. Now, little example. I'm going to give you 3 minutes to think about this on your own, and then I'm going to show you how to solve it. All right, we're going to go over the solution to this now. So we have a function f defined by f of x is equal to 1 over x. So this is the reciprocal function that we talked about earlier. And then the graph of a second function g can be obtained from the graph of f by the following transformations in order. A translation of 3 units in the positive x direction, followed by the translation of 2 units in the negative y direction, followed by a reflection in the line x is equal to 0. So x equals to 0 is this line here, which means that I'm going to be doing negative f of x to get a reflection in the x-axis. Okay. Oh, sorry. The line x equals to 0 is the y-axis. I almost messed that up. So I'm doing a reflection in the y-axis. All right. Trick question. So start with f of x is equal to 1 over x. All right. So f of x is equal to 1 over x. And then let's think about what is happening horizontally. I'm doing a translation of 3 units in the positive x direction. So that means I start by doing f of x minus 3. Okay? And then I'm going to do a translation of 2 units in the negative y direction, so f of x minus 3 minus 2. And then to reflect in the line x is equal to 0, I have to put negative around the inside. So I have f of negative x minus 3 minus 2. And I have to put the negative around the x and the minus 3 because I did that first and now I'm reflecting the result of that. Okay, so that's why there's a minus like that. And this means that the function can be written g of x is equal to f of 3 minus x minus 2. So if I use the fact that f of x is equal to 1 over x, this is 1 over 3 minus x minus 2. And that is my answer. Perfect. Okay. Now part B. Sketch the graph of y is equal to g of x on the axes below. Okay, clearly indicating any asymptotes, whatever. All right. So I just found that g of x was equal to 1 over 3 minus x minus 2. Just give me 1 second here to fix an issue. Okay. So, bum, 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 bum. Hang on. Is there something that I did wrong here? Followed by, yeah, I think, hang on, sorry. I made a mistake in part B when I said that the minus goes in front of the whole thing. Let me go back. So when I shift the function 3 units to the right, the first step, the vertical asymptote becomes somewhere here at x is equal to 3. And then I'm going to flip the whole thing, which means the vertical asymptote is going to become somewhere over here on the left. That's actually just, I'm only flipping the x. I should only be putting the negative in front of the x. I shouldn't have been doing the brackets like that. So it should actually just be this. So it should be negative x minus 3. Which just means I put a negative there instead. Okay, sorry about that. That was an oversight. Now part B. We want to sketch the graph of y is equal to g of x. All right, so I know that g of x is equal to 1 over negative 3 minus x minus 2. Okay, so when do I have a vertical asymptote? When negative 3 minus x is equal to 0, or in other words, x is equal to minus 3. All right, so that is going to be here. At x is equal to minus 3. That's my vertical asymptote. And the horizontal asymptote is going to be at minus 2, because when x gets very, very large, this whole fraction is going to become essentially 0, because the denominator is going to become huge. So I'm going to have a horizontal asymptote at x is equal to minus 2. So we'll put that there. Sorry, that's y is equal to minus 2. And the question wants us to clearly indicate any axes, intercepts, or asymptotes. So we got the asymptotes, but where are the axes, intercepts? What happens when x is 0? I have g of x, or g of 0, is equal to 1 over minus 3 minus 2, which is, because negative 2 is negative 6 over 3, this is negative 7 over 3. So that's going to be somewhere slightly below y is equal to minus 2. So it's slightly there, in which case I'm going to rearrange where I put my asymptote. I'm going to label it here. So I can draw. All right. And any x-intercepts, well, can this function ever be equal to 0? Can I ever have 1 over negative 3 minus x is equal to 2? Well, how is that going to happen? That happens when, if I now multiply both sides by negative 3 minus x, I get 1 is equal to 2 times minus 3 minus x, which means that, which means that 1 is equal to negative 6 minus 2x, or in other words, 2x is equal to minus 7. So x is equal to negative 7 over 2. Right, and negative 7 over 2 is negative 3.5, so it's to the left of the vertical asymptote, so it's going to be right there. Okay, now if I sketch this, it means I'm going to have something like this and something like this, right? Perfect. Any questions about that? Very good. Let's continue. Now, we're getting on to the HL content. So if you're SL, that was everything that we had for you today. Feel free to go and study more questions on the website. But the rest of the session is going to be higher level only content. So we're now going to talk about graphs or transformations where I'm combining a horizontal scale and a horizontal translation. This honestly is pretty difficult. So if I have a function f, if I'm graphing f of ax plus b, what I want you to first realize is that I can write that as f of, if I factor out a, x plus b over a. All right? Why did I do that? It's because if I have ax plus b, then depending on the order in which I do my transformation, I need to make sure I'm doing the multiplication first, so the stretch first, and then the shift. But if I'm doing the shift first, then I do the multiplication or the scaling, then that factor is going to multiply whatever I did with the shift, unless I'm very careful. Okay, so I can obtain the graph of f of ax plus b by a horizontal translation of b units to the left, followed by a horizontal stretch with scale factor 1 over a. So when you have this form, you do plus plus b first, followed by, no, it's got it the wrong way around, I think. Yeah, it's definitely the wrong way around. You either do the scale first and then you add b, or you do the shift first and then you multiply by a. But if you're going to do the shift first, you have to shift by b over a. Okay, and it's just important to get it right. You can do it in either order when you're solving these, but you have to go in the right order according to the question. So let's look at an example in a sec. All right, this is a hard question, and we have time, so I'm going to give you guys 5 minutes to try this on your own. All right, that is time. So we are going to solve this question now. So I'm shown the graph of f of x, and I see that it has a vertical asymptote at x is equal to -3, a horizontal asymptote at y is equal to 2, the x-intercepts -3 over 2 and 1 over 2, and the specific point 3 comma 5 over 3. Okay, so this is a lot of information, and we have a complicated transformation to do. So I'm going to start by thinking about the inside part of the function, okay? So I have, let's say I'm graphing f of 3 minus 2x, okay? I can either think about that as first multiplying everything by -2, and then shifting, if I factor out, shifting by 3 units to the left, or I can start by factoring out -2, figuring out what the shift is, and then multiplying by -2. So I have two different options, okay? So I'm going to start by thinking about what the x-intercepts are. And a useful way to think about how these functions transform when you have complicated transformations is to say, okay, let's call the inside 3 minus 2x equals to k. Okay, because that's the value that I'm putting into f of x, all right? And if I try and isolate x from this, I'm going to find negative 2x is equal to k minus 3, which means that x is equal to 3 minus k over 2. All right? Why is that helpful? It means that every feature that I had at x on the original graph is going to become a feature at 3 minus something on the new graph, okay? So, oh, and by the way, there's also a vertical asymptote at x is equal to 0. It's not labeled because it's on the y-axis, but we have a vertical asymptote at x is equal to 0. So if I plug in now, remember, the function f has a vertical asymptote at -3 and at 0. So when this is 0, this whole function is going to have a vertical asymptote. So when k is 0, so if I plug in k is equal to 0, I get 3 over 2, or if I plug in x is equal to -3, then I get 3, because I do 3 minus minus 3 is 3. So these are the vertical asymptotes. Okay. Let me scroll down and start by drawing those on the graph. So I'm going to have and I'm just going to erase this ugly thing. I know that I'm going to have a vertical asymptote at 3 over 2 and at 3. So let's draw those first. Let's put one at 3 and one at 3 over 2, so halfway there. So those are my two vertical asymptotes. Now, what happens to my horizontal asymptote? Well, I have a horizontal asymptote at y is equal to 2 when I start out, and the function that I am graphing is negative 3f of 2 minus x, of 3 minus 2x, and so I'm going to multiply that by negative 3. So I'm going to have a new vertical asymptote at, if I take 2 times minus 3, it's going to become negative 6. Okay, so that's going to be my vertical asymptote. Sorry, the horizontal asymptote. And let's think also about the axes intercepts, right? I had axes intercepts before at negative 3 over 2 and 1 over 2, right? So those are values of k in this equation. If I plug in k is equal to minus 3 over 2 or 1 over 2, I find my x-intercepts are going to be at, if I do x is equal to 3 minus k over 2, I either have 3 plus 3 over 2 over 2, and that would give me 6 plus 3 is 9 over 4, or 3 plus 1 over 2 over 2, and that's 7 over 4. All right, so what do I have? I have 7 over 4 is slightly below 2, so it's 1.75, so it's kind of like here. And 9 over 4 is 2.25, so and the 2.25 we can say is somewhere roughly there, okay? And I just want to double check something because I think maybe there was a mistake. Oh yeah, there was. This one is supposed to be a minus. It's 3 minus 1 over 2 because I have 3 minus k over 2. So this is supposed to be 5 over 4. Now, I then therefore have one of these at 9 over 4, which is like here, and one at 5 over 4, which is, roughly speaking there. Okay, and now I am more or less ready to graph this because I know that I have an asymptote here, and the shape, by the way, I'm going to have a reflection from the original, so this branch here is going to come, in some way, it's going to be over here, and just based on what I can see here, I know it's got to do this because it passes through that point, and it has to go from the asymptote to the asymptote. Then in the middle, I have this bit, and I've reflected it horizontally and vertically. So I reflect it horizontally, it becomes shaped like that. I reflect it vertically, and it becomes shaped like that. And so it's going to be shaped like this. Okay? And the only thing I want to answer now is what is that y-intercept? So if I plug in 0 into here, then I'm going to get negative 3f of 3. And f of 3, we're told, f of 3 is 5 over 3. And therefore, if I multiply that by negative 3, this gives me negative 5. So I imagine we have some questions here. How did you get a vertical asymptote at x is equal to minus x is equal to 3? Okay. So I want to, maybe now that we've seen the whole solution, I want to explain the key step again, which is this letting k equals to 3 minus 2x, right? Because if I focus on the horizontal portion of the translation, which is f of 3 minus 2x, okay? I want to think about, I know what the graph of f of k looks like. That's just kind of like this, but with k instead of x. And so if I let 3 minus 2x be equal to k, those are the values that I'm plugging into k. But all the features that I'm going to have on my graph are going to happen at certain values of x. So I need to isolate x. And if I do that, I will get 3 minus k over 2 is the x value. And this tells me for a feature that occurred on the original graph at k, where will that feature occur on my new graph in terms of x? And that's what this is, what this equation is going to tell me. And so I took specifically for the vertex, for the vertical asymptote at x is equal to 3, I took this feature, which was a vertical asymptote at x equals to minus 3. So I did 3 minus minus 3 over 2 is 6 over 2, and that's 3. That's how I did that. Absolute values, all right? Before we talk about absolute value transformations, let's just remember what the definition of the absolute value is. So the absolute value is the non-negative number defined by absolute value of x is equal to x if x is greater than or equal to 0, or it's negative x if x is less than 0. So if I do the absolute value of a positive number or of 0, it doesn't change, it's just that number. If I do the absolute value of the negative number, I take the negative of that number so that it is positive, okay? Also, inequalities of functions, all right? These can be solved either algebraically or with technology. It's very important that you remember that when you multiply an inequality by a negative number, the inequality changes direction. So if negative x is less than 1, it's because x is greater than minus 1. So I have to flip the direction and not just change the sign on the right-hand side, okay? And maybe it's worth trying to explain why that is. Let's imagine a number line with 1 here, and we're saying that negative x is somewhere over here. So this is negative x, this is 0, and this is 1. If that's the range where negative x is, then to find x, I can reflect that entire region compared to 0. And if I reflect that, I'm going to get this region. In other words, and this is supposed to be, I didn't draw this very well. That's supposed to be minus 1. So let's say, if I done this properly, negative x would be over here with this entire region. I reflect that entire region, and I get x is less than minus 1, okay? So as an example, imagine I was trying to solve the inequality x cubed minus x squared plus x minus 7 greater than 2x squared minus x minus 7, right? So I subtract the right-hand side, and I bring everything to the left, and I get x cubed minus 3x squared plus 2x is greater than 0. That's nice. I can factor out x. Okay, so I get x. You end up with a quadratic that you could factor. I'm not going to bore you with the details. Once you factor this, you find x times x minus 2 times x minus 1 is greater than 0. Okay, now I have 3 terms all being multiplied together, and I'm trying to figure out when that's positive. The best way to do that is to construct what's called a table of signs, which means I'm going to write along each row one of the terms in my product. So either x, x minus 2, x minus 1, etc. And then each of the columns is going to be the interval, an interval in which the sign of each term does not change. Okay, so how do I construct those? I recognize that x changes sign at 0, x minus 2 at 2, and x minus 1 at 1. So basically, I put a line here. This is 0, that is 1, and that is 2. And I separate the entire stretch of real numbers into regions. So from negative infinity up to 0, then from 0 up to 1, then from 1 up to 2, and then from 2 up to infinity. And what you can do specifically is I know, for example, that x is going to be 0 here, x minus 1 is going to be 0 here, and x minus 2 is going to be 0 here. But then I can think about what the sign of each of these terms is going to be in each of the intervals. So when x is less than 0, x is negative. So is x minus 1, and so is x minus 2. All right? When we're between 0 and 1, x is going to be positive, but x minus 1 is still negative, and x minus 2 is still negative. Between 1 and 2, both x and x minus 1 are positive, but x minus 2 is negative. And then when x is greater than 2, all 3 terms are positive. Okay? What do I do with that then? I make another row for the product of the 3. And I remember that 2 negatives multiplied together gives me a positive. And a negative times a positive gives me a negative. So I have to count whether the number of negative signs in a column is even or odd. If it's odd, I have negative. If it's even, I have positive. So here I have minus, minus, minus. So the first two minuses make a positive, and then another minus makes a minus. And here in the second column, I have plus, minus, minus. So those two minuses combine to give plus. So that's going to be a plus. Then I have two pluses and a minus. That gives a minus. And three pluses just gives me a plus. Okay, and that means that because I'm looking for the interval where x times x minus 2 times x minus 1 is greater than 0, the solution is wherever I have the plus. So from 0 up to 1, not inclusive, and then from 2 up to infinity. So I write my solution 0 less than x less than 1, or x greater than 2. All right, now time for a little HL problem. I'm going to do this one straight away in the interest of time, and also because it's a bit tedious and whatever. I'm kind, so I'm not going to ask you to do it for yourself. So in this question, I have an inequality that also involves absolute values. And these questions are very, very tricky because you have to take into account the different domains over which the absolute values are going to be positive and negative. So what I'm going to start by doing is just drawing a real number line, okay? And I'm going to think about both 5x plus 2 and 3 minus 2x on this number line. So 5x plus 2, 5x plus 2 is going to be equal to 0 when x is equal to negative 2 over 5. So I'm just going to draw that here, negative 2 over 5. And then to the left of that, it's going to be negative, all right? So I'm just going to draw this like a table. To the left of that, it's going to be negative. And to the right, it's going to be positive. So it's going to be positive all over here. And then 3 minus 2x is equal to 0 when x is equal to 3 over 2. So 3 over 2 is over here. Let's put it over here. And therefore, 3 minus 2x, because it has a minus 2, is going to be positive here, and minus here. All right, and I'm just going to add minus, minus, plus for the row above. So now I have basically three intervals in which the signs of 5x plus 2 and 3 minus 2x combine in different ways. So in this interval over here, when 5x plus 2 is positive, then my inequality is going to be negative 5x plus 2, because when 5x plus 2 is negative, the absolute value is going to change its sign. Negative x is greater than, and then 3 minus 2x is positive, so it's just 3 minus 2x over here, okay? And I can solve this, I can expand. I'm going to have negative 5x minus 2 minus x is greater than 3 minus 2x. And let's gather everything I can. I'm going to bring all the constants to the left-hand side, so I'm going to have minus 5. And then on the right-hand side, I'm going to have minus 2x plus 5x is going to be 3x, plus another x is going to be 4x. Okay? So 4x is less than negative 5, which means x is less than negative 4 over 5. All right? So that is for that first interval. In the second interval, both of these things are positive, so the inequality simply becomes 5x plus 2 minus x is greater than 3 minus 2x. And rearranging that, I'm going to get, I'm going to have 4x plus 2 on this side, but then I'm going to do plus 2x is greater than 3. And that's going to give me 6x is greater than 1. So x is greater than 1 over 6. But remember that this is only true in the interval from negative 2 over 5 up to 3 over 2. So this has to stop on the other side at x is equal to 3 over 2. And that has to be exclusive, sorry, because after that it is not going to hold. So exclusive, 3 over 2. Now what happens on the other side? When we are x is greater than 3 over 2, then 5x plus 2 is positive, so it doesn't change. But 3 minus 2x is negative, so it changes sign, and it's going to be negative 3 plus 2x. Okay, so again, 4x plus 2 is greater than minus 3 plus 2x. Simplify as much as I can. I'm going to get 2x bigger than negative 5, or x is bigger than negative 5 over 2. But again, this is only true in the interval where x is bigger than 3 over 2. And so I have to combine that with the fact that x is bigger than negative 5 over 2. Well, if x is bigger than 3 over 2, then it's necessarily bigger than negative 5 over 2. So the solution in this interval is just x bigger than 3 over 2. Okay? And I just realized I made a small typo over here. It's not negative 4 over 5, it's negative 5 over 4. So that's my bad. I just almost missed that. But let's collect what I know now. One thing I want you to notice is if I combine both of these conditions together, you notice that I have for x from 1 over 6 up to 3 over 2, and then x bigger than 3 over 2. And I didn't put the inclusive inequality here, but let's just check what happens when x is 3 over 2 to double check. If x is 3 over 2, and this side is just going to be 0, and 5x plus 2 is going to be 15 over 2 plus 2, and that's going to be 19 over 2 minus 3 over 2 is 16 over 2. So that is indeed bigger than 0. So x equals 3 over 2 is valid, so I can put inclusive here. That's perfectly fine. And then if I collect all of these together, that just means that x is bigger than 1 over 6, or x is less than minus 5 over 4. And if I wanted to write that in interval notation, I could write that as negative infinity up to negative 5 over 4 union 1 over 6 up to infinity. All right, that's how I would write that. So how do I graph f of the absolute value of x? So to obtain the graph of f of absolute value of x, you can think of it either as, in the same sense that the absolute value of x has the piecewise definition, absolute value of x is x for x greater than or equal to 0, or negative x for x less than 0. That means that for when x is positive, f of absolute value of x is just the same as f of x. But when x is negative, then f of the absolute value of x is f of minus x. What does that mean? It means that everything that happened to the left on the function is now going to be ignored. And all that's going to happen is every negative x value is going to copy the value of the function on the right, on the equivalent position on the right side of the y-axis, which means that the graph is now going to be symmetric in the line x is equal to 0 in the y-axis. So we're going to take everything to the right, all of this, and we're going to reflect it onto the left-hand side to find the new graph. Okay. The graph of the absolute value of f of x is a little bit easier because I know that if f goes negative, then I have to reflect it positive because an absolute value is always positive. Yeah, we just mirror the positive side to the negative side exactly. And for the graph of the absolute value of f, what you're going to do is you're going to take the portion of the graph that is negative and you're going to reflect it above the x-axis, okay? What you will notice is that the corners here, in general, are going to be sharp, right? Because when it crosses the x-axis, it is a little bit similar, but it's a little bit similar to the graph of f of x squared, but I want you to focus specifically on these sharp corners. You won't have the sharp corners in the squared case. So just notice that. And that's because if I cross the x-axis like this, it immediately has to reflect. It bounces back with the same slope as on the other side. And that makes a sharp corner. Okay, we're going to start solving this now. So I'm given the graph of g, and I see that it kind of has this bell-shaped curve with an asymptote at y is equal to minus 1 over 2, a maximum at p over 2 comma 1, and then an x-intercept at p, okay? So in part A, on the axes below, we want to sketch the graph of, we want to sketch the graph of the absolute value of g of the absolute value of x. Okay, so what is going to happen when I do this? Remember that sketching the absolute value of a function, doing absolute value of g of x, means reflecting in the anything that's negative to the positive side. Okay, and doing the graph of the absolute value, g of the absolute value of x, is the same as taking the entire side of the function where x is positive and reflecting it to the negative side. So I'm going to actually draw this in two stages. I'm going to start by drawing what g of the absolute value of x is, and then I'm going to take the absolute value of that again. Some things I know are that this point here is going to become a point here because I'm going to mirror it across, and this axis intercept at P is going to become an axis intercept at P again. So if I move that over, it's going to be at 4 and a bit, so it's going to be here. Okay, so my graph is going to look something like this, and you'll forgive my not wonderful drawing, and it's still going to approach that same y asymptote, right? Okay, what else do I have to change? I need to now perform the absolute value on the entire function, which means that any part that was negative becomes positive. So let me draw that in green now. This part is going to become positive, and this part is going to become positive. Okay? Now, what that means is that because I had a horizontal asymptote before it, -1/2, I now have a horizontal asymptote at 1/2. Okay? So let me graph everything that I have now on these axes. I'm going to have still the same graph over here, still the same intercept over here. And then this is going to be here and here. And then it's going to do like this. Boom. It's going to come up and back down. Let's make sure it goes through the point properly. It's going to come up and back down. Bounce here, come up and back down, and bounce again, and do that basically. Okay? So that is the shape of my graph. And that's the answer to part A. We should also label all the points that we know, which is p/2, 1, p, and then -p/2, 1. This is -p, that is p, okay? And this is y is equal to 1/2. Important to label that. Part B. The equation f of x equals q has exactly 4 solutions. Find the possible values of q. So f of x equals q. Remember imagine I was doing this with my calculator, I would graph f of x in one line, and in the next line I would do y is equal to q, and I would look for the intersections of those two things. And the intersections with the line y is equal to q, well, y is equal to q is a horizontal line. So it's going to correspond to the intersections of something like this, okay? And I'm being told that this has exactly 4 solutions, which means it intersects the graph in exactly 4 places. So I'm going to draw a few different lines, and we're going to count how many solutions that gives. If I draw that, I have 0 solutions. If I draw this, I have 1, 2, 3, 4, 5, 6 solutions. If I draw this, I have 4. If I draw right through the maxima, I have exactly 2. And if I draw anything above, I have 0. So let me actually just write the counts down. That's 0, 2, 4, 6, and 0. The only place in which I have 4 solutions is when I'm between this interval here. I'm above I'm above or at the y asymptote, the horizontal asymptote, y is equal to 1/2, but I'm less than the roots, than the maxima, because if I'm at the maxima, then I'm going to be tangent there, and there's only going to be 2 intersections. And so my answer is q is greater than or equal to 1/2, because there's an asymptote at 1/2 means that I can put it at 1/2 and it's never going to touch here. And then it's less than 1. That's the upper bound. Okay, and that is my answer. Is there a preferred method for writing out the solution set? Either as an inequality or using the inclusive-exclusive brackets. Both are fine. Both are completely fine. Yeah, both are totally fine. I think maybe the solution brackets will force you, if you're writing them out, to really double check whether things are inclusive or exclusive. I think it's easy when you're writing out an inequality. I could easily have written here, I could have done this and forgotten to check whether the 1/2 was inclusive or not. Whereas if I'm writing out with the brackets, every bracket I have to think, oh, is this one a square bracket or a normal bracket? And just having to do that thought is going to force me to check. So I like to do the solution sets with brackets for that reason and that reason only. The IB is fine with both. All right, now, oh, which bracket is what again? Yeah, I guess I can explain which bracket is which. Remember that the inclusive bracket, this one I would write as 1/2 up to 1. And the 1 would be exclusive, so I would write it with this bracket. Okay? And if you ever have infinity or negative infinity, you have to put these brackets. You can't put an inclusive infinity, all right? That's just another warning, all right? So that's the same as inclusive, and that's the same as exclusive, all right? Now, graphing f of x all squared. This is a little bit similar to the graph of the absolute value of f of x, except that the corners here are not going to be sharp. What I do know, though, is that the square of anything is always going to be positive because functions are real valued. And that means that the function is always going to be above the x-axis. But it's not going to have a sharp corner because when something gets close to 0, you get this behavior where small numbers when squared become smaller. And that makes a kind of smoothing effect close to the x-axis. All right, so that's why you get these rounded corners and not the sharp corners that we saw earlier with the absolute value. Also, above the x-axis, there are changes. We're not just reflecting the part that's negative. We have to square all the values, which is going to, in general, bring things up if they're above 1 or bring things down if they are below 1, right? So if this was like 3, 2, then this would become 3, 2 squared would be 4. But if this was 3, if it was 3, 0.1, then actually I would have something like this in the end because this would be 3, 0.1 squared, which would be 0.01. So it doesn't always get bigger, right? It doesn't always get bigger. It gets bigger, though, if for anything that's bigger than 1, okay? And I believe this is the last kind of transformation that we have to talk about, which is graphing 1 divided by f of x, all right? And this is a really annoying one to think about, but it does show up not too infrequently for just kind of random functions that you might have, okay? Yeah, it looks a bit scary. But let's pause and remember what we know about rational functions, okay? I know that I'm going to have vertical asymptotes when the denominator is 0, okay? And I know that I'm going to have a horizontal asymptote for certain behavior when the function goes to infinity. So I want you to imagine the graph of 1 over f of x, all right? Each value on the curve, I'm going to do 1 divided by the old y to get the new y, okay? So points where f of x was 0, if f of x is 0, then the new function is undefined there, and I'm going to get a vertical asymptote because 1 divided by 0 is undefined, and 1 divided by something close to 0 gives me a vertical asymptote. So the zeros of f of x become the vertical asymptotes of 1 over f of x. That is step 1, okay? Also, if the absolute value of f of x is large, if f of x basically is either very, very plus infinity or minus infinity, then 1 over f of x is going to be very small. And that means I will get a horizontal asymptote and y is equal to 0. So that means that the vertical asymptotes of f of x become the horizontal asymptotes of the new function, okay? So that is step 2. And yeah, now the local maxima and the local minimum are going to flip, okay? So if I have a maximum at a comma b on the graph of f, then it's going to become a minimum at a comma 1 over b, because let's say I have, a graph that does something like this. When I do 1 over b, I'm doing 1 divided by the value. So the larger the value, the smaller it's going to be. And I'm going to get something that looks like, well, there's going to be an asymptote here. So it's going to be like this, and then like this, and then like this, okay? And I'm going to get this maximum becomes this minimum, okay? And you're not going to get a question that tells you to just like from scratch kind of do all this. These questions will have multiple parts and will ask you to show this and show that. So in theory, this is hard. The questions are not usually crazy. Okay, and in a similar way, a minimum becomes a maximum, all right? So minimum at c comma d becomes a maximum at c comma 1 over d. All right, with that all said, let's do an example. So let's say I'm trying to sketch the graph of 1 divided by x squared x squared plus 2x minus 3. All right, and I know that the denominator is 0 when x is equal to 1 or x is equal to minus 3. Those are the factors of that quadratic. So I'm going to have vertical asymptotes at x equals minus 3 and x is equal to 1. That's step 1. Now, I also know that the quadratic x squared plus 2x minus 3 has a minimum at negative 1 comma minus 4. And you could find that by completing the square or by, plugging in the axis of symmetry, and you would find that the quadratic has that minimum or that vertex. And that tells me that the graph of y of 1 over the quadratic is going to have a local maximum at minus 1 comma minus 1 over 4, okay? Also, as x squared plus 2x minus 3 gets larger, then y is equal to 1 over that is going to approach 0, right? So that means that I'm going to have a horizontal asymptote at x is equal to 0. That's everything I know. That's everything that I need to know. And that allows me to graph, because now I know that I have a maximum here at negative 1 comma minus 1 over 4, which means that I have to be, I have to be concave down between here. And if this was the original quadratic, by the way, I know that it's going to still be positive over here and still be positive over there because there was no sign change. So I have the graph here of y is equal to g of x. It's this kind of piecewise function. And it's equal to minus 2 as a horizontal line up until x equals to minus 1. Then it slopes up, and then it levels off at 2 again. So I want to graph first g of x squared, and then 1 over g of the absolute value of x. God, that's pretty awful. So let's start with x squared. What do we know about x squared? Everything's going to become positive. I'm going to have a smooth x-intercept for every original x-intercept, and all the values become squared. So in particular, this line 2 here, y is equal to 2, is going to become y is equal to 4 because I'm squaring it. So it's going to become like this. Okay, and actually I'm going to draw it with a perfect straight line because otherwise it's going to get ugly. A nice straight line. The same thing happens for this line y is equal to minus 2 because minus 2 squared is also 4. So that is going to give me this. Okay, now between those two, I have a straight line and it's being squared, and I know that therefore I'm going to have a smooth, a rounded x-intercept at 0. So what does it look like? I'm going to have basically a parabola here. I'm going to have a parabola that does this and comes back and meets it, okay? That is g of x squared. All right, now 1 over g of the absolute value of x. That sounds like a bit of a nightmare. So first, on the graph above, I'm going to actually just draw g of the absolute value of x. Remember, I take everything that's positive and I reflect it to the negative side. So I'm going to have this, basically. Okay? And then I'm going to do 1 divided by that. Okay? So where is this thing 0? This thing is 0 at 0. So that means I'm going to have a vertical asymptote at x is equal to 0. And it's positive everywhere else. So all the arms are going to be positive. So I'm going to have something like this and that, The question is, where are the horizontal asymptotes going to be? Well, this function levels off at y is equal to 2. So when I do 1 divided by that, it means it must be leveling off at y is equal to 1 over 2. So I'm going to have a horizontal asymptote at y is equal to 1 over 2. And that means that I'm going to have and it's not actually a horizontal asymptote because it actually literally reaches that value. I'm going to have a straight line at 1 over 2 here until minus 1. Also a straight line here. And then after that, the function is going to do its asymptotic behavior and go up like that. Okay? And this is y is equal to 1 over g of the absolute value of x. No horizontal asymptote because the function remains a straight line. So yeah, there's no horizontal asymptote because the original function doesn't get closer and closer to something. And it doesn't go to infinity. It's just that we know that the function, the original function is equal to 2 for everything less than minus 1 and everything bigger than minus 1, then bigger than 1. And therefore the new function is going to just be equal to 1 over 2 at those values. So it looks a little bit like an asymptote, but it's actually not an asymptote because it reaches the value and it stays there. It doesn't move. So good question. There is no horizontal asymptote. So with that said, we're now ready to tackle one of the I think trickiest topics in the IB that is not super commonly examined on the syllabus, but it is there, which is rational functions where I have a quadratic denominator. So I have f of x is equal to something ax plus b divided by some quadratic. What do I know? I know that a rational function is going to have vertical asymptotes when the denominator is 0. So when my quadratic is 0, I'm going to get horizontal asymptotes, all right? When do I get horizontal asymptotes? Well, I just need to, when vertical asymptotes, I just need to solve the quadratic that I have in the denominator. We know how to do that. You'll either find 0, 1, or 2 roots, and those will be your vertical asymptotes. Now, what happens horizontally? we notice that because x squared is a higher power than x, when x gets very big, cx squared is going to dominate over ax. So if I let x is equal to 1,000,000, I'm going to have a times 1,000,000 plus a small number b divided by c times 1,000,000 squared, and 1,000,000 squared is just much, much bigger than 1,000,000, and therefore you're going to have a horizontal asymptote at y is equal to 0 because you have this x squared, which is more important. Okay? Also, there's going to be an x-intercept at x equals negative b over 2a, which is when the numerator is 0 and it changes sign. All right? What else do we know? We know that if the numerator and denominator share a root, this has never shown up on exams, by the way, but in theory, I want you to know this. If one of the asymptotes of one of the zeros of the denominator is also a zero of the numerator, then you won't have an asymptote there because you would have 0 over 0. It would still be undefined, but it would just be 0 over 0 and not an asymptote. Mind you, it has never showed up on the exam. And a question says, if the numerator and denominator share a root, why wouldn't we cancel out the factors? It's a very good question. If I have the function f of x is equal to x minus 3 over x minus 3, that's not actually equal to 1. It is if I say x is not equal to 3. But, and it looks almost a little bit silly. Why can't I just cancel? Because literally the function isn't defined as 1. It's defined as this fraction. And this fraction is not defined when x is equal to 3. 0 over 0 is not defined. You can only do that factoring. You can only divide, cancel out the factors when the factors are not 0. Remember, you're not allowed to cancel factors that are 0. So this function is not actually the same as 1. You can't just cancel the factors. But that's a good question. So you would end up with a hole. You would end up with a hole here at x is equal to 3. So, example. Let's say I want to sketch the graph of x minus 1 divided by x squared minus x minus 6. Okay? So the denominator is a quadratic. I can factor it as x minus 3 times x plus 2. And that's going to be 0 when x is equal to 3 or x is equal to minus 2. So those are my vertical asymptotes. X is equal to 3 or x is equal to minus 2. Okay? Also, the numerator is going to be 0 when x is equal to 1. So that's going to give me an x-intercept at 1. Right? I also know that there's going to be a horizontal asymptote at y is equal to 0 because I have a linear divided by a quadratic, and the quadratic is just much bigger at infinity. And I'm going to start tracing on the negative side. How do I know it's negative? Honestly, I probably just plugged in a value. If I plug in, let's say, negative 3, I would do y is equal to negative 3 minus 1 over 9 plus 3 minus 6. And I would find negative 4 over 6, and so it'd be negative. So I know it's negative on this side, so I'm going to trace a negative. And then I know that it changes sign at the root because x plus 2 goes from minus to positive. So I continue from the positive side here. I go through my, what's it called? The x-intercept at 1, and I continue down to the asymptote there. I change sign again, and I continue. And that's how I would sketch this. A question says, algebraically, when solving an equation like this, would we cancel? You cannot cancel if you don't know if x minus 3 is 0, okay? You have to specifically mention, well, it depends on the question. It depends on whether or not x could be equal to 3. If it could be equal to 3, then you have to write down that x could be equal to 3, right? In the same way that if I have, let's say I have, when I have x times x minus 3 is equal to 0, it doesn't mean that x minus 3 is 0. It means that one of the two is 0, right? So you have to be very, very careful when you're dividing to make sure that neither of those things is 0. Let's move on. All right, we have an IB style example of this, which is to sketch the graph of 3x minus 1 divided by 2x squared minus 6x minus 20. Okay, so how much time? We have no more than 45 minutes. I'm going to start with this straight away. So I'm being asked to sketch the graph of y is equal to 3x minus 1 over 2x squared minus 6x minus 20. So I have a linear divided by a rational, a rational function with a linear divided by a quadratic. So what I'm going to need to do is find the roots of the quadratic, because when the quadratic is 0 and the denominator is 0, I'm going to have vertical asymptotes. So let's start by solving 2x squared minus 6x minus 20 is equal to 0. I can divide everything by 2 to make my life a little bit easier, and I'm going to get x squared minus 3x minus 10 is equal to 0. Now, I'm going to factor this by inspection. I'm looking for two things that multiply to minus 10 and add to minus 3. So I see minus 5 and plus 2 do that. So I'm going to do x squared minus 5x plus 2x minus 10 is equal to 0. And that means that I have x times x minus 5 plus 2 times x minus 5 is equal to 0. Or in other words, x plus 2 times x minus 5 is equal to 0. So this has roots when x is equal to minus 2 or x is equal to 5. So if I just plot those quickly on the diagram, I'm going to have a vertical asymptote right here and a horizontal asymptote right about there. You don't have to sketch exactly, to scale, but just getting a rough idea that 5 is bigger than 2 is always a good idea. So let's just draw that like that and draw this like this. Okay, not a perfect diagram, but so that's one thing. The other thing I have to think about is the numerator. So what happens to 3x minus 1? When is that going to be equal to 0? That's going to happen when x is equal to 1 over 3. All right, and if the numerator is 0 and the denominator is not, so the function is well defined, then the curve is going to go through the x-axis. There's going to be a root. So x equals 1 over 3, I'm going to put right about here. There's going to be a root there, okay? What about the y-intercept? Okay, the y-intercept happens when x is 0. So if I plug x is equal to 0 into this equation, all that's going to be left is the minus 1 over the minus 20, because all the x's are going to disappear. And minus 1 over minus 20 is just 1 over 20. So it's going to be somewhere here, a small positive number. Okay. Now, is there anything else I can figure out here? No, I think that's all the information we need, because those are the only intercepts and the only vertical asymptotes. It's worth mentioning that because I have an x squared in the denominator and an x in the numerator, my horizontal asymptote is just going to be x is equal to 0. So you don't really need to draw that. You just make it clear that your function is approaching that. And maybe you can say x equals to 0. You can write it down just to be extra clear. But I at least know that my curve is going to come down from the asymptote. It's going to pass through both of these points, and then it's going to go back down to this asymptote because there's no other sign changes, so it can't go back up. And because I know that the quadratic has roots there, it's going to change signs. The whole function has to change signs at both of those vertical asymptotes, and the only sign change for the numerator is here. Okay, so I know I go from minus to plus there, and I know that just it's the only way that I can go through both of those points that I just found. And because I have to change signs on the other side of the asymptote, I must be going like this, okay? There's no other choice. And the same thing has to happen over here. I must be going back to the positive case, and I will get something like that. And let's just make sure that I label all my points. This is 1 over 20. This is 1 over 3. This is x is equal to 5, and this is x is equal to minus 2. And just to be sure, I'm going to write y is equal to 0 to indicate to the examiner that I do actually know where the vertical asymptote is, just in case they feel like being strict on a particular day. Oh, this one is not fun. Rationals with oblique asymptotes. So if I take the opposite of what I was just talking about, which was when I had a quadratic in the denominator, and instead now I put the quadratic in the numerator, then first of all, I'm going to have a vertical asymptote when the denominator is 0, which is when, dx plus e is equal to 0, so x is negative e over d. And then what I notice, if I perform polynomial division, then the oblique asymptote of f of x is going to have the equation y is equal to something times x plus, and this should be a different c than this. It should be, let's say, capital C, which is determined during polynomial division. So I know nobody likes polynomial division, but let's see an example. Let's say I'm doing 5x squared minus 3x plus 2 divided by 3x minus 1. Okay, so what I'm going to do is I'm going to start, I have 5x squared and I'm dividing it by 3x minus 1. So I have 5/3, because I have 5 and 3, so 5/3 of x is the first thing I write. And then I'm going to subtract in the first row 5 over 3x times 3x minus 1. And that's just going to be negative 5x. It's going to be minus 5x squared, and then plus 5 over 3, 5 over 3x, 5 over 3x. Okay, so I add that, and I keep my plus 2, and my new total is negative 4 over 3x plus 2. Okay, If I divide that again by 3x minus 1, I have a second term now. 4 over 3 over 3 gives me 4 over 9, and there's a minus here, so minus 4 over 9. That's what I put there, minus 4 over 9. And then if I subtract out what I'm left with, I subtract out, I do minus 4 over 9 times 3x minus 1, which is the same as doing plus 4 over 3x minus 4 over 9. And that leaves me with a remainder of 14 over 9. All right, and the remainder actually doesn't matter. The only thing that matters really is this this dividend that I find, which is the 5 over 3x minus 4 over 9. Because that's going to make what we call an oblique asymptote, which is an asymptote that is a straight line that actually has a slope, okay? So if I were to graph this function, I graph 5 over 3x minus 4 over 9. I graph my vertical asymptote at x is equal to 1 over 3. And then the rational function is going to still have asymptotes, but they're going to be curved like this towards the oblique asymptote, okay? Very, very tricky topic. Doesn't show up super often, but it is on the exams. Could we cover synthetic division? So if you want to do division, the session on polynomials, which is next week, I will do a kind of more examples and a deeper dive on actually doing this process. So that's next week if you want to show up for that. Okay. Now, the final question of today, which is one of these oblique asymptote questions. I'm going to give you, what will I give you? I'll give you 5 minutes to try it, and then we'll continue, okay? So in this question, I'm trying to sketch the graph of a rational function whose numerator is a quadratic and denominator is a linear. Okay, so what are some things I immediately know? When the denominator is going to be 0, that's at x equals to 1 over 2, I'm going to have a vertical asymptote. So I can start by drawing that. That part is easy to figure out. The rest is going to be not so easy to figure out. The question wants me to find asymptotes as well as axes-intercepts, so we can think about the axes-intercepts next. My y-intercept is going to be when x is equal to 0. If I plug all of that in, I'm going to get negative 1 over 1. So it's just going to be 1. Put that there. That's 1. This is x equals to 1 over 2. And now, where am I going to have x-intercepts? Well, my x-intercepts are going to be when 6x squared plus 7x minus 1 is equal to 0. Or in other words, 6x squared minus 7x plus 1 is equal to 0. A bit easier to deal with. I can factor that. It's going to be 6x minus 1 times x minus 1 is equal to 0. So I'm going to have an x-intercept at x is equal to 1 over 6, which is here. So that's 1 over 6. And at x is equal to 1, which is over here. All right, that's 1. Now, what other asymptotes am I going to have? I'm not going to have a horizontal asymptote because I have an x squared in the numerator and an x in the denominator. Instead, I'm going to have an oblique asymptote. And an oblique asymptote happens when you have a quadratic divided by a linear, or basically in general, when the numerator has a power of x 1 higher than the highest power of x in the denominator. And it is a consequence of the fact that I can divide the fraction using polynomial division and write it as something ax plus b plus a remainder c divided by 2x minus 1, okay? And now I can immediately identify what a is going to be by looking at the first two terms, because the a is going to be just the ratio of the coefficients of the first two terms. And I can show you why that is by putting all of this over a common fraction. So if I were to write this expression with the unknown a and b and c over a common fraction with 2x minus 1, I would get ax times 2x minus 1 plus b times 2x minus 1 plus c, okay? And if I expanded that, that would be 2ax squared, and then minus ax plus 2bx, so plus 2b minus ax, and then the constants are going to be plus c minus b. Okay, so plus c minus b. Now, that is still being divided by 2x minus 1. And you do indeed see that this 2a has to correspond with the minus 6. And so a must be equal to
minus 3. And then if I compare the coefficients of the x's, I have 2b minus a is equal to 7. And 2b is therefore equal to 7 plus a, which is equal to 4. And so b is equal to 2. Right? B is equal to 2. So my oblique asymptote is ax plus b is equal to negative 3x plus 2. And that is going to look something like, if I graph it, it's going to go through 2, and it's going to have a slope of minus 3, and it's going to have an x-intercept when x is 2 over 3, so it's going to be something like this, okay? And it's not exactly to scale this diagram, but that's okay. I don't actually need to find the value of c. It's not going to correspond to anything on my diagram, so there's no need to even think about it, but you could find it just by looking at the equation. Okay, and now because I know where all these points are and I know where the asymptotes are, it becomes relatively easy to sketch, because I know that I have to start near the asymptote, I have to come through these points and go back to near the asymptote, and I'm going to change sign, and I'm going to come down like this, through the x-intercept and back towards the asymptote, okay? Let's just make sure that I label this for the examiner as negative 3x plus 2, and I've labeled everything else. Yeah, perfect. I am good. This is my final answer.